So I will talk about direct anthropic bound on the weak scale from supernova explosions. This is a work done with D'Amico, Urbano, Star, and Xue. Star means that I am the substitute to Alfredo. I hope I remember what we did, and anyhow, all of us were outside of our expertise, so it would be good if somebody can check these results, because they involve one important topic, which is understanding why nature has three very different scales: the vacuum energy, the weak scale, and the Planck mass. A lot of theorists worked on this, believing in naturalness. And now the idea was that the cosmological constant will be zero for some reason to be found, and the X must come with new physics that protects its mass. And the good theory was found and was supersymmetry. However, experiments found instead that the vacuum energy is small and non-zero, and the X is alone with no new physics. So it's nice when facts give you a kick in the back and push you in a new direction. But this time it was not so nice, because the new direction has the word anthropic. So many physicists don't like to work on this. The ordering of scales is so important that it has anthropic relevance, and a different understanding emerged. So maybe there is some theory with a number of vacuum huge enough that accidentally some vacuum has a small vacuum energy and weak scale, and all of them are realized by inflation in multiverse. Weinberg, not a crackpot, many years ago observed that a vacuum energy 100 times bigger than what it is would have prevented galaxy formation, giving a solid anthropic argument. And more recently, Agrawal, Barr, Donoghue, and Seckel noticed that a weak scale 10 times bigger than what it is would have prevented chemistry. So let me review their argument. In the standard model, the proton is the lightest stable baryon. Neutrons decay if free. Neutrons in nuclei become stable, and many nuclei exist. All of these thanks to a numerical accident that involves the weak scale and the QCD scale. So if we make the weak scale smaller, then the proton becomes heavier and decays. But we actually need to go in the opposite direction to understand anthropically why the weak scale is not bigger. If you make the weak scale bigger by a factor of few, then the mass difference becomes so large that neutrons decay even in nuclei, and then the only chemistry will be hydrogen. Increasing the weak scale by more, you get some even sharper argument. All of this depends on fermion masses, which in the standard model are Yukawa times vacuum expectation value. So this bound actually involves this combination. And then the big question is if this anthropic bound is enough to explain why there is no new physics at the Large Hadron Collider. And I think the answer is no, because even if all this multiverse stuff is real, its most likely outcome will not be what we see. First, if in this landscape there is a theory where the weak scale is naturally small, then such theories will be more likely. It's the usual fine-tuning argument. However, one can imagine that the supersymmetry might be absent in some landscape, or maybe in string theory it's almost always broken at the Planck scale. So this is not a strong argument. A stronger argument is that a standard model-like theory with bigger weak scale compensated by smaller Yukawa, such that masses remain constant, will be less unnatural and as good as the standard model. So And some people even consider the extreme limit of a wickless standard model where the Wick scale is pushed up to the Planck scale. This is a paper by Harnick, Cripps, and Peretz. So we remain confused because what we see, the standard model, seems unnecessarily tuned. And unless there is some direct anthropic bound on the Wick scale. And this talk is about the possible bound of this type that would involve the Wick scale, Planck mass, and QCD scale, no Yukawas. I omit order 1 factors, which actually are of order 100. So we have to look at physics and see in which cases electroweak interactions give big effects that may have anthropic relevance. And there are 2 cases, and in both, non-trivial physics arises because this combination is of order 1. The first is Big Bang nucleosynthesis, where neutrons survive to thermalization and to decay because this factor is of order 1. So clearly, if the Wick scale were smaller, neutrons would get exponentially suppressed. However, what we need is the opposite direction. And in the opposite direction, bigger Wick scale will make more neutrons, so less hydrogen. These authors, Hall, Pinner, and Ruderman, argue that this might be an anthropic bound. However, I am not convinced that this is a solid argument, so I will not discuss this. It's important. Let me instead discuss that maybe there is a second possibility about core collapse supernova explosions that seem to have both crucial characteristics. First, critically depend on the Wick scale, and second, be anthropically needed. Let me discuss why. So what is the role of Wick interactions? According to the standard picture, for example, discussed in this review by Janka and others, what happens is that there is a star with oxygen and other material outside, iron in the middle, there is a collapse. This collapse gives nothing until neutrinos come out and push the material out, and then this is what gives the explosion. And these neutrinos are real, and simulations now seem to validate this mechanism for explosion. The doubt is that maybe there are other mechanisms for explosion that involve maybe rotation or magnetic fields. I am not expert of this. Second is about anthropic relevance. This explosion spread oxygen similar elements that seem produced almost only in this way with doubts, and furthermore, they seem elements necessary for the chemistry of life. And of course, this is a complicated topic. I am not expert, but at least I can review this astroperiodic table, which is just the periodic table colored according to what produces each element. So, for example, hydrogen and helium are gray. They are produced in Big Bang nucleosynthesis. Cosmic rays that hit add a few more protons and make a little more. These core collapse supernova are making essentially all of oxygen and other elements, which are believed to be primary elements in biology. Also, it makes important elements considered to be of secondary importance. Other explosions tend to make heavier elements. I am not expert, but the general reason is that these other explosions are meltdowns of nuclear reactions that can proceed up to the ground state, iron, leaving a negligible amount of light nuclei. So all of this is unsafe, but important. So I assume that it's true. And next, I study if what happens to supernova explosion when the weak scale is valid. I keep all the rest fixed because this is the direction I need to explore. And one must disentangle dynamic adjustment from tuning to avoid doing CRAP. For example, stupid statements like that the length of legs is fine-tuned to reach the ground. So obviously this has anthropic relevance, but obviously it's due to dynamics. So we have to avoid getting confused by this sort of possible mistakes. And one example of this dynamical adjustment happens in stars. So let me open a parenthesis. Weak interactions are relevant in stars. For example, this is the sun, and this is the sun photographed seen in neutrinos. However, there is no anthropic bound from stars, because if you change the weak scale, cross-sections change, but they have a strong exponential dependence on the temperature. So what happens is that the temperature changes a bit, adapts, and star keep doing slow burning. Nothing changes. Let me just tell that some authors, this is a parenthesis inside the parenthesis, Howe, Groch, and Adams, claim that there is this anthropic bound from stars on the Planck mass. No time to review why it comes. So I close both parentheses and I go to supernovae. Supernova, so there is an iron core. It can no longer burn. It's sustained by electron degeneracy pressure, but weak interactions convert electrons to neutrinos, and then the inner part of the core crashes, and the mass of the part that does the collapse is the Chandrasekhar mass. The time scale of weak interactions is faster than the gravitational time scale of the object, which is about a fraction of a second. By the way, what I say will be validated by running a public code by Ott and co-authors that employs the spherical approximation. So at least we are not completely wrong. Okay, so we now have this inner core collapsed to nuclear density. I here provide the order of magnitude estimates just to understand physics. So for example, the mass is the Chandrasekhar mass, and it also is the energy of the supernova. This is the number of nucleons, and this is the radius of the core. Next, there is a detail. Before cracking, nuclei try to resist a bit like nuts. This means, more technically, that nuclear interactions have a repulsive term that is strong enough to start a rebounce shock wave. So in this picture, this is time, this is radius, this is the collapsing inner core. At some point here, nuclear interaction manages to give some reaction. Something goes outside, but instead of giving an explosion, it stalls at a radius of around 100 kilometers after about 1 second. So nothing happens. The key point is that exactly at the right moment, neutrinos are still inside and come out and push until bang, there is the supernova explosion. And numbers are so critical that this explosion only happens not in spherical approximation, but when you do simulations with all coordinates. So let's now next change the weak scale. First, what happens to the neutrino trapping time? It grows with this combination of parameters. White grows. It's not simple, but also not too much complicated. Inside the inner core, the density is constant, so it's just the usual random walk estimation. And you get this factor. Outside, it's more complicated. Now, neutrinos are trapped even beyond the inner core, where the density is going lower and lower as you go farther. So you need to know how the temperature behaves. You impose the trapping condition, and then you get how the radius of the neutrino sphere, which is the area within which neutrinos are trapped, depends on the weak scale. And you get the temperature from doing a very simple estimates. And then by using the usual black body formula, you get the power emitted the neutrinos and then the time to escape. So these order of magnitude estimates are simple, are not trivial, and they are confirmed by running numerical codes. So again, we are not totally wrong. Next, what happens to how much neutrinos push matter outside? Naively, one would guess that if you increase weak interactions, neutrinos push more because they interact more, but this is wrong, because here there is a dynamical adjustment that you must take into account. The final answer is that trapped neutrinos make roughly one scattering after exiting from the neutrino sphere. Then the total energy and momentum transmitted by neutrinos to matter outside is the total energy they have times order 1, independently of the weak scale. And there are details. For example, there is a region where neutrinos hit matter, but neutrinos can also cool matter by just escaping. So there is one region where matter is heated and one where is cooled. This will not be much relevant because essentially nothing changes with respect to the standard picture. Then let's go to the final result. So we change the weak scale. What changes is 1, the neutrino cooling time, 2, the radius in which neutrinos are trapped and give energy to matter. This is all what changes. So if the weak scale is very, very, very big, then obviously neutrinos are not trapped, they come out, nothing happens. If the weak scale is a bit bigger than what it is, maybe twice the standard model up to 10, but here this is just random numbers, then neutrinos are trapped, but not much. They escape too early with a time scale different than the time scale of the shock, and they don't manage, we believe, to produce an explosion. Here is the standard model, and here is a range around the standard model. Neutrinos come out, are trapped, and come out at the right moment, and come out from the right place behind the shock wave to push, and then this mechanism is efficient enough to get the explosion. Finally, we can also consider small values of the weak scale, so not relevant for the anthropic understanding, but we study in any case. Here, neutrinos are trapped in a big region and are trapped a lot, and they escape, but when it's too late. Now the party is already over, neutrinos slowly exit, they do nothing. Furthermore, the shock wave, we expect that will be inside the neutrino sphere and the gain radius. So that's one additional reason why they cannot give energy. And we did the simulations in spherical approximation, running a public code that we hope we understand, but we are not expert. We have a lot of plots, and based on these plots, I simplified the physics telling what I told. So I believe we are not completely wrong, but it would be really important if experts could confirm that we are right enough. Finally, one final slide about the general theory of landscape. The question I want to address, if a landscape really allows for having an accidentally small vacuum energy and weak scale. One who like to study string theory, but nobody knows if really it gives a landscape. So instead, one takes quantum field theory. And here the practical difficulty is that if you have to search among a huge number of aqua, you don't know how to do it in practice. It's trivial, but it's important. So here in this paper by Nima with Dimopoulos and Kakru, they introduced the toy landscape with a few hundred of scalars. Each one has 2 minima. So the number of minima is exponentially large. And then this shows that you can get many values of the vacuum energy. We want to see if one can also get many values of the Higgs mass. So we found useful to introduce this biquadratic interaction, because then we are able to do some mathematics and deal with a huge number of aqua. And let me tell what we find about the possible light scalars. Some minima have a light scalar that, however, has a big VEV, and this is bad squared. Well, first, because it's not the Higgs, the VEV must be small. Second, because vacuum decays very fast, as we'll discuss in the next line. Other minima have a light scalar and 0 VEV or small, and they are bad because, as I said, vacuum decays catastrophically fast. Why? Because the potential accidentally has a small mass, but in general, the cubic is of order of the Planck scale, something big. So this potential means that vacuum decay is immediate, completely bad. The only good case is if somewhere there is a vacuum with accidentally small mass and small cubic. You could do with a tuning, but so the only little observation we make is that some scalars cannot have any cubic, and then this is what can give light scalars and stable vacua in the landscape. So you need something like the Higgs. So it can work. We check that vacuum decay is slow enough. A non-trivial result is that the number of channels is not exponentially large, but it's small. Who is the Higgs changes inside the landscape? So it's difficult to get to say anything about Yukawas. Probabilities can be Gaussian, but could also be completely different. So period, summary, this idea can work. So conclusions, direct anthropic bound on the Wii scale can make sense of what we see at the Large Hadron Collider if this is a true anthropic bound, and we argued that it might come from core collapse supernova explosion if first they are driven by neutrinos, and second, if core collapse supernova explosions are needed anthropically to produce oxygen and similar elements. Supernova dynamics is complicated because it's tuned. We derived simple scaling confirmed by spherical simulations. We cannot perform the real work, and I hope that experts can get interested and check, because this issue, anthropic with a bad word, is related to understanding mass scale signature, which is a very big issue in theory. And furthermore, we have shown that the toy QFT landscape can do everything is needed. And of course, the difficult question are there predictions. We predict that the Higgs has no cubic, which is not a great prediction. I'm sorry, I stop here. Fast talk.
Okay, thank you. So we have time for the discussion, especially if there is some supernova experts. It would be great to hear.
Could I ask if V is increased, Alessandro, would that not also affect the pre-supernova evolution? There is neutrino energy loss even before the last moments, where of course it becomes very important.
So we believe, we guess, maybe it's safer, that in the immediate early phase is changed, but nothing anthropic is happening. This is somehow confirmed by simulations. And we also believe that in the much earlier phase of slow burning, there is some change, but not big. No, we believe that the only place where there is a big anthropic shift is what I said.
It's true that earlier when there is equilibrium, things can adjust to cope with any shifts like that. That's possibly true. Yes. Thanks.
Crossing fingers.
Yeah.
Alessandro, could you please, can you hear me?
Yes.
Could you repeat what are the conditions you choose for the explosion? Because it's spherical symmetry, in principle, you don't have explosion, no? What are the?
Yes. So
I understand what are the conditions
that
you choose.
So okay, we don't get any explosion. We talk a lot, but we don't get any explosion.
This I believe. Okay, then.
So we believe that we understand the physics. We believe that if somebody would run real simulations outside the spherical symmetry, we believe that what would come out is this. Explosions only happen in some range of the weak scale, somehow around the physical value. And we also believe it would be important to really do this. Now, when you really do, it's a total mess because codes are the best they can do for the physical value. When you change the weak scale, you can easily get the nonsense from existing codes. So it's not easy.
And you, sorry if I can. So usually it's Andrea here. So usually when because they cannot get an explosion, they can trigger artificial. So usually what they do, for example, when I mean they want to see how the temperature and the density changes, they just the eating rate, they usually increase artificially the eating rate of the neutrino in just some phase to trigger the explosion and see.
So this is what people did when running codes in spherical approximation. But now there are people able of running codes with all the 3 dimensions. And this is, for example, this is a recent paper by Janka and others. And without doing this kind of cheating, they can get explosions with similar energy to what is observed.
So this paper is very recent, right? Because actually, like last year or 2 years ago, also there was the other paper by Kfir and Guido in which they were saying that, stressing that no explosion was seen in simulation yet, right? So
we have Guido here, I suppose.
Yes. Yeah. Well, I mean, the papers with Kfir refer to an alternative mechanism that doesn't rely on the neutrino mechanism. And yeah, that is not very much analyzed. And in fact, I had a discussion with Thomas, who I see here the day, in fact, that his paper appeared. I mean, I still believe that mechanism is interesting. And in fact, I think that our paper with Fear was more a paper pointing out to like phenomenologically different prediction for the neutrino from supernovae. So it actually stresses more that if we are to see the neutrino spectrum of flavor and energy, we can actually know what's the mechanism for explosion of a supernova. Regarding this, the paper with Alessandro, yeah, also referring to Paolo, and I don't know who was the other, but so we decided not to cheat, not to increase the heating, because I mean we really because I mean how do you increase the heating? Like since we are changing anyway the neutrino interaction, it would be messing up with the physical effect we wanted to show, and so we decided just to show the non-exploding, simulation, and we were looking at the scaling, right? And so, as Alessandro explained, we had a physical picture and we were trying to confirm the scaling by simulations.
May I comment? Here's Thomas Janka.
Yeah, hi Thomas.
I think, hi. Thank you very much for these nice presentations. I enjoyed it, both of them. I mean, I think you were right not to play with parameters artificially, because you can easily be misled. I mean, we do that, as somebody mentioned, when we want to investigate the outcome of supernova explosions and large numbers of stars, and do that by one-dimensional modeling. We use an artificial energy deposition, a change in parameter, changing the deposition in 1D models, which is maybe fine for astrophysical purposes to get a principal understanding. But for your purposes, where you really need to explore the scale, the range of change for this scale parameter, I think that would be highly risky, and you could be easily misled. You could do this now with a three-dimensional modeling, and what somebody said was certainly right, that three-dimensional models now give explosions. That's not so recent. It has been seen already for a couple of years that with 2D and later 3D modeling, we got explosions self-consistently, neutrino-driven explosions. What is new now in this preprint, which is mentioned here on the slide, is that we now can run the models, the 3D models, long enough to see the explosion energy saturating to the final value, which was not possible before because of the expense of computer time. You could do this study changing the parameter, the coupling parameter in the 3D models, but it would still be very time consuming. So this is not a project you can do as a side project, just beside your ordinary ambition. It has to be done dedicatedly by a postdoc maybe, or a student spending a couple of years on this project. So I would not say it's easy, but it's feasible, and it could certainly be interesting, but it would have to be defined exactly what the questions are, and what the scale, the range of scale in this parameter is, which should be explored. Otherwise, you are lost. I mean, maybe first a 2D model would be sufficient to get a rough idea, but certainly it has to be done in 3D. I'm not 100% convinced, however, that the progenitor models wouldn't change. It may also be a more subtle issue that needs to be investigated, whether changing the neutrino cooling, the pair production cooling, wouldn't change convective processes and burning shells in the progenitor evolution, so that the progenitor structure itself already changes significantly. And I'm not sure that I believe the arguments given in the talk that the pre-collapse evolution is independent of a change of the weak scale. Thank you for your patience listening to my points.
Thomas, before you go, that was precisely my concern. But the question is, if there is quasi-equilibrium in the pre-supernova phase, then would there be internal dynamical adjustment to compensate for the rate of pair cooling?
Yeah, that's a good question, which I actually, from experience and from a kind of intuitive approach, cannot answer. It would have to be tested. I don't think that this question was explored. I just know that rather recently there was a mistake in the weak cooling rates, just by incidence. A collaborative group of mine has implemented a mistake in the cooling rates, and there were significant changes in a certain range of progenitor masses. And this mistake was actually not a big one, so it was a relatively minor difference in the pair cooling rate, and it made a significant difference in the iron core masses in a certain range of progenitor mass.
No, that's important. Thanks. Thanks for leaving.
Yeah.
No, by the way, now what we find in the initial phase is that now if now the weak scale is changed, somehow the temperature changes until still weak interaction made to do a similar job. And we have detailed the results now from numerical simulations, but we don't understand the details. That's the situation.
But when you say progenitor evolution, did you run the progenitors up to the moment of core collapse?
And with,
no, this not. But
no.
we studied a bit stellar evolution.
Yeah, but in which phase, and which code did you take, and what effects did you take into account? I mean, studying beyond the hydrogen burning phase, in particular late stages of stellar evolution to the core collapse phase, is not such an easy game. There are public codes now. MESA, for example, is, as far as I know, able to do it to some degree of reliability. But have you done that?
No, and we have been told that we should not trust too much these codes for big stars.
Well, yeah.
Yeah, I mean, MESA, I think, is in a pretty good shape right now. It has been developed over years, and I think some groups have applied it already to produce some a handful or so progenitor stars for core collapse studies. But I cannot, from my own experience, I cannot comment. So I can only recommend to go to the website of the MESA code and check out whether there is any information on that, or contact some groups who have used it. But that may be possible. But still, I mean, for answering the question whether the progenitors change, I think you have to run the models up to the stage of the onset of collapse, and only then you can tell whether the initial conditions of the core collapse simulations are already changed.
Okay, thank you. I mean, now we actually took the standard progenitor, and we had some argument that they wouldn't change much. Yeah, if I remember correctly, I had a quick look at the MESA, and it wasn't easy to adjust weak interactions alone, but maybe by now somebody has done it. Now that's a good point. It's a fair point. We just had some rough argument that they wouldn't change.
I mean, the late phases speed up a lot in the evolution, so maybe there is not quite enough time for this adjustment anymore. On the main sequence, yes, you have a lot of time stars can adjust, and maybe there's a relatively large insensitivity to these weak interaction effects. But during the late stages, as I said, from this one experience where the cooling rates were changed a little only, because of this mistake, it tells me that it may not be like that. So that has to be looked at.
Okay, yeah, thank you. Yeah.
Overall, I think it's an interesting problem. And basically, I have had a look at the paper only this morning when you sent me an email. I had a quick look. I mean, I basically agree with your points and the directions you find. I think, at least from a quick judgment, I would say it's probably basically correct what you see. Of course, what that does in multidimensional simulations is a different question. That has to be really done in multi-D, and then the feedback will give you the exact range of change which is possible. It may be little, actually. It may not be much, which already can make a significant change to the supernova explosion. And then secure this whole supernova scenario will be difficult because rotation and magnetic fields are probably not the general solution to the explosion problem. We have to rely on the neutrinos because predictions say that most stars at the onset of core collapse should rotate relatively slowly. That's not engraved in stone. We cannot look into these stars, and binarity and stellar evolution itself already with a lot of phenomena is a complicated business by itself. But at the moment, we need this discrimination of slow rotating normal supernovae and fast rotating extreme cases for understanding why normal supernovae are on the energy scale so much different from hypernovae and gamma ray burst supernovae.
Thomas, can I ask a question while you are online? Does it worry you that the only supernova we ever observed in neutrinos, SN87A, that there was a tension between the observations by Kamiokande and by IMB, and even gross quantities such as the total energy emitted and the typical temperature of the neutrinos did not give consistent answers. There's about 3 and a bit sigma tension between them. Does that worry you?
Yeah, I mean, of course, data from one event and statistically sparse data in particular are difficult to interpret. I don't think that it changes anything of the situation, independent of whether this worries somebody or not. I don't think they can find an explanation for that because we can't reproduce the event. We have just to wait for the lucky case of an exgalactic supernova. And at the moment, at least for my scientific activity over the past 20 years, I would say, not hoping for a next galactic event in the next days. I went a different route, and we tried to connect the explosions to other observables. And everything we can deduce from the current models is that the neutrino-driven scenario with the ordinary input, let me say, based on the standard model physics, seems to explain observables pretty well. So we get a pretty good understanding of asymmetries in supernova explosions, of basic nuclear synthesis in supernova explosions, energies. Now the recent paper was mentioned, which we have now shown in 3D self-consistently, that we get an explosion energy of the order of what supernova 87A had just by neutrino heating. We have other approaches where we can see that we get neutron star and black hole masses reproduced reasonably well when we compare them to the ensembles of cases observed. So we are on a pretty good track to understand astronomical parameters, not necessarily having to rely on this one event where we saw neutrinos from. Let's really hope that we get a galactic case in the very near future with a high statistic supernova observation, which then will tell us in detail what was going on during neutrino trapping and when neutrinos heated the explosion. But that is a hope at the moment.
Fair enough. Thanks.
For the next collider.
Okay, so thank you very much. So I think we can stop this session here. And so just a second.
Okay. Bye.
Thank you. It was very interesting.
Unusual time, 8:30 p.m. So after dinner for those of you that are in Europe.
Thanks.
Bye-bye.
Bye.
Bye.
Bye-bye.